So we look at number 3 on page 37, and we identify, hopefully, a substitution, at just first glance. That's the ideal thing, but it doesn't always play out that way. So you take a stab at it. I'll say x to the 4th minus 25. And whether you play it out in your mind or on paper, it really doesn't make a difference to me. It's just you need to verify that the derivative of that is going to help you cancel out the other part of the integral, the part that you're not calling u. So du would be equal to 4x to the 3rd dx, because 25 goes away. All right. This needs to go, and so does this. And that's good news, because that's the meat of my differential equation. All right. So I'm just going to clean it up by dividing out the 4, and get 1/4 du equals x cubed dx. All right, so I'll write my integral with, instead of the x cubed dx, I'll write it as 1/4 du. On the bottom, instead of the square root of the mess, it's the square root of u. I just want to address my bounds. All right, so the bounds would be handled by my u relation, the u that compares x and u together. So I want my new bounds to be in terms of u, so I don't have to reverse substitute later on. So plug in a 2. We're looking at, what, -9? Plug in a 1, you're talking about -24. I don't know, maybe you'd want to work in terms of x. Those don't look too nice. Right, but we'll see where it goes. Right, so those are my new bounds. I'm going to clean up my integral and make it 1/4. That would be u to the -1/2 du. And that's going from -24 to -9. All right, if we're doing this using an analytic approach, I don't have high hopes that my final answer is going to be something that's nice and neat, but yeah, we'll see. Anti-differentiate, u to the 1/2. We're taking the 1/4 and dividing it by that 1/2, so it's the same as multiplying by 2. So 1/2 u to the 1/2. And you can check by taking the derivative over the interval of -24 to -9. All right, so looks like we're going to have radicals that involve negatives. So we'll express our answer with negatives under radicals. So it's going to be, by fundamental theorem, 1/2 times -9 to the 1/2 minus 1/2 times -24 to the 1/2. All right. Now that 1/2 power is the same as the square root. Right. So square root of a negative number, that's going to involve some imaginaries. We don't do much of it in this course, but you have some experience with it, so it shouldn't be the end of the world. And also, it sort of justifies why we're doing this by hand, because this is the exception. For every topic, there's an exception. Do it with your calculator. Except, if you have negatives under radicals, you might get an error message. Right? Although if you put your calculator in the A+BI mode, which we'll talk about later, you could get a cleaner answer. Anyway, 1/2 times, this is 3i, minus 1/2 times radical 24 simplifies down as the product of 6 and 4. So 2 radical 6, so 2i radical 6. And so a little bit of housekeeping. 3/2 I minus I radical 6. All right. The meaning of which you'll address in much more detail in much more advanced math classes. Okay, it's trying to really kind of flesh out this area under a curve, on a particular interval. So how do imaginary numbers come into play? Okay, that's a different story for a different course. But just knowing that you can have imaginary answers is really all we need. All right, so if you zoom, let's go 100%, so I can see the next problem. All right. Now, the next one's got e to the x, 1 over e to the x. It's just a big old mess. So it's a question of what are we going to call u there. And then the bounds, those are fun to look at also. Well, let's just focus on u for a minute. That makes it sound like I really care. So, take a stab at it. One thing you might want to consider doing, this is 1 to alpha, the Greek letter alpha. It's just saying some unknown upper bound. If you don't feel like drawing the alpha value, just use an A. I don't think anybody ever loses any sleep over that sort of thing. So, e to the x, I'm sure somebody loses sleep over it. I'm just saying that I don't really. E to the negative x, and then e to the x minus e to the negative x dx. All right, so maybe write it like this before designating your u. I'll go back to the larger zoom in a second. I just want people to see the full solution of number 3. So yeah, you have a little bit of an issue here. I'm going to let u equal to e to the x. It's going to be e to the x plus e to the negative x. Is it just e to the negative x, e to the x minus e to the negative x? And so we have choices. So my recommendation would be to make one. That is a choice. And then carry out that choice and see where it takes you. Right? So when you make that choice, just bear in mind that the u that you decide upon should help to simplify things. So if I just let u equal e to the x, I can substitute out a lot of stuff. But will it make the situation easier to handle? Maybe, maybe not. So maybe try something a little bit more elaborate. I mean, it's been pretty commonplace that when we have fractions that the denominator ends up being the u. I mean, it's not always the case, but it happens pretty often, so let's try that. In the absence of any other, any better ideas, give it a shot. All right, so I'm going to take the derivative of this and see if it helps. So du would be equal to, the derivative of e to the x is just e to the x, minus the derivative of e to the negative x is e to the negative x times negative 1. When you take the derivative of exponential e, you keep it as is, and then multiply by the derivative of whatever your exponent is. All right, in this case, our exponent's negative x, derivative of which is a negative 1. Zoom, I'll go back to page width, so you have a better look at that. All right, clean it up, and I need a dx at the end. Clean it up and see where the journey takes you. Du equals e to the x plus e to the negative x dx. Well, that's precisely what I needed.
Again, why you the denominator instead of...
I could have made it anything I wanted. I chose the denominator because it seems like it's very often the case that when we have fractions that it's the denominator in some capacity. So I was like, you know what? I don't know what it is. It's oftentimes it's the denominator, so let me just go with that and see where it takes me. Fortunately, it took me to a good place. It actually took me to a really, 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 really good place, because this can now be replaced with just a du. All right. So this is going to give me a new integral. The bounds will have to be changed in a second, but it's really just du over u. All right. So we could address the bounds. You do this one of two ways, just like I talked about in the last one. You can convert over your x bounds into u bounds, or you could leave it as is and then reverse substitute and put original bounds back in. So the last one I did the change of variables. So this time I'll just leave it as is. So I'm going to leave it boundless. I'm going to write it as basically an indefinite integral, because it would not be appropriate to write the bounds of 1 to alpha, because those are not related to u. So I'm going to leave it as is in this form and take the antiderivative, reverse substitute, and then I'll throw the original bounds in. If you want to, if you're very, peculiar or particular about notation, maybe you write something like u of 1 and u of alpha, just to state that there are bounds, or at least remind yourself that there are bounds that should be there. You're just not going to state what they actually are in terms of u. Right? So it's up to you. That you have free reign for. But the antiderivative of 1 over u is the natural log of u. All right. We know that this would have to be over a particular interval, so I'll stick with that notation. Ah, I hit the wrong button. A little flash forward of what's to come. Oh, I missed a problem too. Undo that. So I'll just write u of 1, u of alpha. Hovering over the wrong thing here. So now that I have my antiderivative, I can reverse substitute. It's ln of e to the x minus e to the negative x, since it's now back in terms of x. And it's weird because I have like lots of vertical lines everywhere. Those vertical lines are absolute values. This one is the such that. We're going on the interval of 1 to alpha. So now I can do my plugging and chugging. Not much chugging, just plugging. E to the alpha minus e to the negative alpha minus ln of e to the first minus e to the negative first. And there's some things you can do to clean it up a little bit, but nothing really worthwhile. There's no width. Right, but with a variable upper bound.
You just e to anything minus e to the negative anything is 2.65 something.
It always works out? Oh. Interesting. Pause. On here. Alright, so let's do a zoom 6 to start, see where we're at. There you got a little asymptote action going on there. Oh, but it looks like after 1 it levels off. Oh, gotcha. Right, but it should still be accumulating more and more area. Yeah, but...
I don't know.
Right. Right. So on your lower bound, should still be variable though, just based on what I'm looking at. Because let me just get my window going. I'll go from, because it's 1 to really anything, but I don't need a lot of it. So let me just do like, I don't know, like 2. Yeah, so if I were doing 1 to 2, it would be on this interval. So the height wouldn't change, but you'd still have a change in x, so the area should still change. So you should still get something variable. Huh. I'll have to look into that. There might be something to what you're saying, but I need to really think about it. Good.